Welcome to another exercise in a workbook statistics, this time with an exercise on the binomial distribution. Let's have a look at the exercise. Here we have, to send out advertisements, you get a set of 40,000 addresses spanning all of Germany. From experience, you know that on average, 23% of the addresses are faulty and cannot successfully be delivered. Your computer randomly selects 5 addresses that are contacted. Then, first question, what is the probability that all of the addresses are faulty, meaning all of those 5? What is the probability that at least one of the addresses is faulty? And finally, in one day, 2,000 flyers are sent out. How many of those will not be able to be delivered? Well, before starting with this, why are we going to use the binomial distribution here? Well, what we know is that this probability here usually will not change if we just picked a wrong address. So this remains fixed, and whenever we have a fixed probability, then we are going to use the binomial distribution. We could also argue that, well, if it randomly selects 5 addresses, it might select the same address twice. Usually a computer wouldn't do this, smart computer, then we would have to use the hypergeometric distribution. But the problem with the hypergeometric distribution is we do not have the numbers necessary to work with the hypergeometric distribution. We just have the probability. We have no large n, no large k. So that's more of a pragmatic approach. So we're simply missing the information we need for the hypergeometric distribution. So well, in either case, we're going to use binomial distribution here. And in part A, what we are looking for is that 0 are faulty. So we have a probability P of random variable being equal to 0. We know from the exercise text the probability for this event happening is 23%, and we have a sample size of 5. Then we're going to use these 3 values, the 0 for small k, this for small p, this for small n, in a probability function of the binomial distribution, giving us this result. Small n over small k, p to the power of small k, and then 1 minus p to the power of small n minus small k. This one is 1, this one is 1. So for the last part, we get as a result 27.07%. So roughly more than 27% chance that none of the addresses which are sent out, or which are addressed in this case, are faulty. Well, that was part 1. Let's then directly go to part 2, to B. And in B, we want to have the probability that less than 4 and less are faulty. Well, in this case, we could do 2 things. We could go calculate probability of it being 0, 1, 2, 3, or 4. That would in total be 5 probabilities. Or we could calculate the counter probability, 1 minus, then we have larger than 4. Well, with a sample size of 5, we only have one possible outcome, one integer, which fits this criterion, and that's the 5. So we're going to work with the counter probability in this case. We have the same probability as before. We have here a sample size of 5. So we're going to just insert these 3 values then into the probability function of the binomial distribution, which looks like this. Again, this one and that one being 1. We can easily get the result by calculating that, subtracting it from 1, giving us a final result of 99.94%. So the chance that in a sample of 5, 4 or less will be faulty is 99.94%. Well, that was more or less also part B. So let's turn to C, to the final part of this exercise. And here we're looking for an average. However, an average for 2,000 mailed flyers. So we have to multiply the probability of an address being faulty with the amount of flyers being sent out in a day. Well, if we do this, if we multiply 2,000 and 23%, we get 460. So we can assume that 460 flyers will not be delivered to anyone because the addresses are faulty in one way or another. Well, that's then everything to this exercise. I hope you enjoyed it. I say goodbye and see you next time.